division of a monomial by yeah, we had dividing stuff. Of a polynomial by a monomial. I know. This last year I assigned everything. This year I just assigned odds on the first chunk and evens on the second chunk. But here's all of the answers. So you're looking at 1, 3, 5, 7, 9, and then you're looking at this column right here. Yes, I know I have all of the answers there. I did more work than you. Go me. But you did. If you did what I assigned, then that's great. Questions on any of these? Does anyone want to see any of these done? 18 and 22. Hold on. You said you want to see 18 and 22. Okay, anybody else? You want to see any of these other ones? Going once, twice. Okay, so Danny, what did you do for 18?
For 18, I had x to the power of 2
Yep.
minus x to the power of 1.
Yep.
Or it was x.
Yep.
But then the minus 1 just wasn't there.
Well, what's 3 divided by 3? 3 divided by 3?
1.
3 divided by 3 is 1.
Yeah.
So you've got, the first two are good, but then this, 3 divided by 3 is 1, not 0, so you have to have a minus 1 here at the end.
Right, okay. I did that.
And then 24 is going to be similar, I'm willing to bet here.
No.
Sorry, 22 is going to be similar here. Because if you have 5x, or should I do the whole thing? Here, let's do the whole thing.
X minus 2x. Instead of x minus 2. Maybe I just threw in an extra x there. I don't know.
Here's what you did. You would have done 5x squared. Here, let's look at it here. 5x squared over 5x minus 10x over 5x. My 5s are going to cancel. X squared over x is going to give me x to the power of 1.
Okay.
And then 10 divided by 5 is 2. And x to the 1 and x to the 1 is going to cancel out.
Okay.
Leaving me with just x minus 2. Okay, so this leads us into flipping the page. And we're going to review factoring, which we've kind of done before. We factored things back when we were looking at radicals, because we wanted to simplify radicals. Remember what I'm talking about here?
Yeah.
Like if I have the square root of 48, what did we do with that? Okay, if I said we had the square root of 48, and I want to write that as a simplified radical, what would I do? Carolyn?
Oh, I would say you just do like a factor 3. Yeah.
Do you want to do it?
Okay, so 8 and 6. And then out of the 8, 4 and 2. And out of the 4, just 2 and 2. And then out of 6, 3 and 2. And yeah.
So is this ringing bells? We remember doing this way back in exponents?
Mm-hmm.
Who said no? Because we definitely did it. Okay. Out anybody? It's probably Rebecca. Or Armand. No, it wasn't Armand. Manraj. The two people who were away. They don't remember. Sorry if you're watching this, you two. So what we did, this section down here, what did we call this? Do we remember what this was called? Sorry, I heard it.
The prime factors.
The prime factors, or the prime factorization. Absolutely. So we were then able to write this thing as, so we could, if we wanted to, write this thing as 2 to the 4 times 3. Because I have 2 times 2 times 2 times 2 times 3. And this thing right here is the prime factorization, because 2 and 3 are both primes. This I multiplied together, it would give me 48. You see how that happened?
You could also say you always pair that, don't you?
Yes, when we're going back to this, we would then just pair these. So then this would be, I'd have these two would give me a 2 out front. These two would give me a 2 out front, and then the root 3 would stay there. So when we were doing the radical, this was the method we took. When we're just breaking up this number here, we get this thing here. This is called the prime factorization. We follow? Is this something we've seen before? Hands up if you've seen this before in middle school.
No, not in middle school. In this class.
In this, but not before this class?
I don't think so.
Okay. Okay?
Yeah.
So what we're going to add, okay, so we didn't write it like this. Okay. So what we're going to do is we're going to add to this the idea of greatest common factoring. Have we done greatest common factors before? Is that a word that makes sense to people? Maybe some long to okay. Okay. Well then let's take a look here. What I want to do for each one of these, I got these numbers. Let's practice we're finding the prime factorization of this. I've got 8x squared y. What is the prime factorization of this? And I want to write it like this.
Oh, okay.
What we're going to do is we're going to take that coefficient and we're going to break the coefficient up like we broke up 48.
Yeah.
So Carolyn,
2x and y. Maybe we can break that into 2, like this, 5,
2 and
6, 4.
2 and 4, and then 4 can be broken up into 2 and 2. Okay?
And then the x is just x plus x.
So then the x squared stays, x squared is just x times x, so we can leave it as x squared. And y is just going to be y. So I broke up my 8 into its prime factors here, 2 times 2 times 2. And then my x squared and my y are just going to stay there. So what I've got here is I've got 2 cubed x squared y,
Yeah. Okay.
where the exponent here just tells me how many of each factor I have.
How come we do that?
Sorry?
Like, why do we put 2 x squared y?
Because of where we're going. So let's do the same thing here with 12xyz. What is the prime factorization of this? Yes, Carolyn.
2 squared times 3 times x minus x.
How'd you do that?
12 is 12 times 3, and then before so that was 2 times 2. So you have 2 squared times 3, and x minus x.
Cool. Does what Carolyn did make sense to all of us? Okay. Next one. Who wants to take a look at this? Ten meet. Nope. Is that 10 meet 10? Yes, it was 10 meet 10.
Should I tell you?
Yes.
5 squared 2x x to the power of 5 dt.
Absolutely. Does anyone want to see how she did that?
You don't type pi squared times 2 x. So we can always do this separately.
You could write it as 5 squared times 2, yeah. I like to write them with the prime factorization. Prime's getting larger.
So what about with the?
Okay, so 50 can be broken up into 25 times 2. And then 25 is going to be 5 times 5. So my prime factorization then is going to be 5 squared, because I got 5 times 5, times 2, times x to the 5 z cubed. So it's going to be 2 times 5 squared, x to the 5 z cubed. Danny.
For the next one, with the factoring for negative 20, could be like 4, negative 4, and 5, or 5 and negative 5. But then.
Well, let's break them up into 3 then. Let's go negative 1. Let's pull that guy out.
Oh.
And then 4 and then 5.
Okay.
And then 4 is going to be broken up into 2 times 2. So this guy's then going to be what?
Negative 5 times 2 squared.
Oh, I see.
Yeah, I like to write it as like increasing prime numbers, but yes. You could write it as negative 5 times 2 squared.
So where did the?
But that is like, if we write, so we're gonna
Oh, I understand why you did that. No, I would always toss the negative 1 out front and then leave everything else, all the other prime factors positive. Again, that's just convention. That's just how I like to do them because of what's coming. Because I know what's coming here. Yeah.
If we wanted to solve it as negative 4 and 5, and then negative 2 and 2, and we got negative 2, 2 and 5.
No, you want a group where you want to group what you can group here.
But would you be able to do that with those numbers without having a negative 1?
Well, you couldn't then combine them. No, you couldn't. Because you'd have to combine, like you want all our 2's together, and you wouldn't have, so we want our we want that 2 squared there.
Well, we could say negative 10 and 2, and then out of the negative 10 we could do negative 5 and 2, so we have 2, 2 is just negative 5.
You want all of the other prime numbers to be positive. Pull that negative, for the sake of where we're going,
Okay.
pull that negative out. This is how we typically write the prime factorization.
Okay.
From this, the question I'm going to ask you is this. What is the greatest common factor of these 4 numbers? So am I understanding this right? You have not talked about common factors before this year. Elementary school, middle school, you never talked about common factors. Where? When? So then what's a common factor? You've forgotten. A long time ago it's forgotten. Okay. Not a common multiple. But it's similar. Like when usually you learn about greatest common factors when you learn about lowest common multiples. Usually that happens at the same time. So what a greatest common factor, so let's go do some definitions first, and then we'll come back and find the greatest common factor here. To factor something, a polynomial, that means what we're going to do here is we're going to break it apart. We're going to break the polynomial up into the objects that multiply to it. That's what we're trying to do here. This is looking a little blurry. Why is that? Because it's not necessarily just numbers. There's going to be variables. These are I'm talking about the objects, mathematical objects. Some of them will be numbers. Some of them will be variables. Some of them will be like full expressions. But to factor a polynomial means we take the polynomial and we break it down into the things that multiply to give us our polynomial. Like 8 is 2 times 4. Or 2 times 2 times 2. We're breaking up 8 into the pieces that multiply back together to give us 8. We're going to do the same thing with these polynomials here. Well, if I want to, this technically is a polynomial, a single-termed polynomial called a monomial. Some of us forgot. And so if I want to break 8x squared y into its factors, or its prime factors, that's what I did here, 8x squared y is the same thing as 2 cubed times x squared times y. So I've broken this up into the objects, in this case numbers and letters, that multiply back together to give you what we started with. So GCF here stands for the greatest common factor. Which is the largest factor shared by, how do I want to say this? Say several polynomials. That is what the greatest common factor is. And a common factor just means, or two common factor, like what we're going to do here now, this just means we're going to pull out the factor found in each polynomial. Or in sometime in each term within a polynomial. So if I've got these things right here, let's go back and look at the prime factorizations of these four objects here. For each one of these things that I've now boxed, these are the prime factorizations for each of those objects, mathematical objects. The question now that we need to figure out is what piece or pieces do these four objects all share? 10 meet. They all have at least, is it at most 1, 2, or they have multiple 2's? Well, this one has how many 2's? 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 So the greatest number of 2's found in all of them is 1. So the greatest common factor is going to involve 1, 2. Now let's look at the variables. Carolyn. Yeah, because this one has 2 x's. This one's got 1 x. This one has 5 x's. This one has 3 x's. So the greatest number of x's found in all of them is 1. Is there anything else common to all 4 of them?
No.
Carolyn says no. 10 meets hand, shot up, and then shot back down.
Are there all
Are we satisfied with what Carolyn said? There's nothing else shared between all 4. So then what this means is the greatest common factor of these 4 terms is this, 2x. Because that is the largest thing that I can pull out of or factor out of these 4 mathematical objects. Cool? So typically in the past, this is what you would have done for greatest common factoring. You would have seen a couple numbers and then you would have pulled out what was common among them. Am I going to get you to practice that later? I should. Is that what I'm hearing? So instead of pulling it out of multiple separate objects, what we're going to do now is we're going to look at individual terms within a single polynomial. So here I've got 4x plus 8, and I want to pull out the greatest common factor from this polynomial. So now we have to ask ourselves, what is the largest thing that I can divide out, is effectively what we're doing, from each term? Danny.
Do you just solve them first and then?
There's nothing to solve here. It's just 4x plus 8. That's.
No, but do we have to convert the 8 to
So there's a few ways you can do it. You could break this thing down into its factor trees, but when the numbers are small, assuming you guys know your multiplication tables, this is something that you could theoretically do in your head pretty easy. 4 I could break up into 2 and 2. 8 I could break up into 4 and 2, and then 4 is 2 and 2. So then what could I pull out of 4 and 8? 2 squared. Well, 2 squared is just 4. So we can recognize here, what is the biggest number that I can take out of 4 and 8? The biggest number I can take out of both is 4. Because 4 divides out of 4 and 4 divides out of 8.
Okay.
Or you could see here, look, I have 2 2's and 2 2's. 2 times 2 is 4.
Yeah. Okay. Yeah.
So we use the factor tree to kind of show us why this works, but we don't have to use it very long. In fact, I would love us for to be able to get away from it. But when the numbers are big, sometimes it's hard. So what we're going to do is to break this thing up into its common factors, we're going to take the factor that's common to both 4x and 8, and we're going to pull it out front. What we're going to do is this. 4x plus 8 is going to equal, now you said the greatest common factor was 4. So I pull my 4 out front, and now if I divide my front term by 4, what do I have left? I have x left. And if I divide 8 by 4, I have positive 2. So if I'm going to break 4x plus 8 up into its common factors. If I redistributed it, I would get what I started with.
Oh, that's the goal.
Because 4x plus 8 is equal to 4 times x plus 2.
So the next one, then you make 5 plus 4 and not.
Yeah, so I can pull a 5 out of both because 5 can divide out of 5 and 10.
Yeah.
And I'm going to be left with a plus 2.
Right. Okay.
Because the GCF is 5. Relatively straightforward, yes? Okay, let's do another one. Let's keep going. What's this? What can I pull out of 6a and negative 18? Yes. Sure. Let's make this a little bit more, it's just a smidge more challenging. What would I do with something like number 2? So I put my greatest common factor out front. I put my brackets down. Good.
Wait, why?
3y actually.
Yes. Why?
Why what?
Can you just walk through it?
Okay. So Aminette figured out the greatest common factor was x. I can't pull anything out of 3 and 4 because 3 is prime
Okay.
and 4 isn't divisible by 3. I've got 1x here and 1x here, and I've got 1y here, but I got no y's here. So the only thing I can pull out of both is going to be a single x.
Oh, okay.
So the x goes out front. That's my greatest common factor. And I'm going to divide by x, divide by x. I'm going to get 3y plus 4.
Okay. I was just expecting to get a number.
Doesn't have to be.
Okay.
3 is relatively straightforward. What's my GCF for 3? Because we're trying to separate it up into the things that multiply together to give us the polynomial that we're starting with. And so to break up the object, I'm dividing it. That is the literal definition of the word division, to break up. So we're dividing out the greatest common factor. Harwin. Careful with this one. Why 3? If I pulled out a 3, I would be left with negative x and a negative 2. Because they're both negative, I can actually include that negative as part of my GCF. So negative 3 is going to be my GCF. And then I'll be left with, so negative 3 divided by 3 is, sorry, negative 3 divided by negative 3 is, but it's 1. So that's just going to be 1x. And then negative 6 divided by negative 3 is positive 2.
What you said? You said something because it has a negative sign. You can keep that out. But I just thought
Because
negative
both of
sign
these
was put there.
because both of these terms are negative,
Right.
I can include the negative as part of my greatest
That
common
was-
factor.
If it was negative 3x plus 6.
You mean like question number 9? Bottom right. Where one of them's negative and one of them's positive. We can do the same thing.
Number 3.
We just did 3.
No, but positive 6.
It's the same as number 9. We'll get to number. We'll do it when we get to number 9.
We'll do number 9 and then come back to number 3.
No, what you're asking me, you're asking me to change 3 a particular way, but I've already changed it with question number 9. So when we get to question number 9, I will address your, but what if we did this question that you love to ask. Okay, number 4, what would I do? What's my GCF? 2, which means I would be left with 2 times a plus 7b. Cool. Number 5. What's my greatest common factor there? It's 2a. Because I've got an A and A and an A in each term. So it's going to be 2a. And what do I have left? B plus C plus 2D. Love it. Do we see how that happened? Okay. Number 6. Who wants to do it? Someone, not Carolyn, because she clearly knows what she's doing. You're volunteering, Danny? Do number 6?
4x. Wait.
You're saying 4x is our GCF?
Yeah. But then there's no. It's just 4.
No, you were right. You were right. It is 4x.
No, but then the squared x.
Squared just means I have x times x. So how many x's are multiplying here? 2. How many are here?
1.
So how many how many x's are common in both terms? There's
1.
There's one x found in each term.
Right.
So x is going to be part of my GCF.
It's x minus 3. But then where's the squared?
Done.
No, wait. Explain that. You said.
So you did it correctly, so I don't really want to explain it.
Times x minus 12 times x. Wait, I don't. The common. But then where does the other x go? There's another x.
The x is part of the greatest common factor here. Like, look, what would happen if I multiplied this thing back together? Like,
Oh.
if I took my
Okay.
factorization and I put it back together,
Right.
if I distributed this back in, what's 4x times x?
4x squared.
4x squared. What is 4x times negative 3?
12x.
Negative 12x. So that means we must have done this correctly, because when I recombine it,
Then it works.
it is what I started with.
That's nice you can double check that.
Absolutely. Number 7. Someone other than Carolyn or Danny. Yes, I see that hand. Chelsea. 5xy is your greatest common factor. That is correct, leaving you with what?
W plus 2x plus 4.
Careful with the second term. 2z plus 4. Good. Anyone have a question about what Chelsea just did? Because 5, 10, and 20 are all divisible by 5, and there was an x and a y, an x and a y, and an x and a y. Love it. Someone who is not Chelsea, Danny, or Carolyn, do number 8. Emma.
The greatest common factor is x squared y.
You betcha it is.
So at the end it would be x squared y times, in brackets, 2y squared, take away 4, plus 5xy.
Questions about what Aminette did? Harwin? Sure. Which part? Like with the GCF?
Yeah.
Okay. So again, look at what we want to do to figure out the GCF when we're involving variables and coefficients. We want to figure out what pieces are common to each. So is there a number that I can divide out of 2, 4, and 5? No. So there's going to be no number there part of our GCF. Now, how many x's do I have here? I have 2 there. How many here? And how many here? So what's the largest number I can pull out of all 3 terms? 2 of them. I can pull out 2 from here, 2 from here, and 2 from here. So I put my x squared up front, and now I look at my y's. How many y's? What is the largest number of y's found in all 3 terms? 1. This one has 3, this one has 1, this one has 2. So my greatest common factor then is going to include a y, a single y. There are no other variables here, so my greatest common factor then is going to be these 2 x's, the x squared, and this y. So it's going to be x squared y. Now what I'm going to do is I'm going to divide x squared y out from every term. 2x squared y cubed divided by x squared y. The 2 is going to stay, the x squareds will cancel, and y cubed over y is y squared. The next one's going to be similar. I've got x squared y, but I'm dividing it by x squared y. Yeah, and this one here, the 5 stays. I've got x cubed divided by x squared, leaves me with 1x. And y squared divided by y, leaves me with 1y. What I'm doing now is I'm not actually, the reason we did dividing yesterday is because we're doing it again today, but I'm not writing it down in as much detail as I did yesterday. Does anyone want to see that level of detail? Okay, so then what's actually happening here is this. We pull out the greatest common factor, and then we're going to divide plus 5x cubed y squared. Sorry. We're going to divide each one of those terms by x squared y.
Oh, okay.
Is what we're doing here. Here, my x squared y's cancel. So my x squareds cancel, and this one's going to leave me with y cubed, or y squared. Here, my x squareds and my y's cancel, leaving me just with -4. Here, my y and my x squareds are going to cancel with that guy, leaving me with 5xy.
So the next one, the negative.
And then the last one is going to be number 9. I've got -2ab to the 5 plus 4a to the 4b cubed. So Danny, this is similar to what you were asking before. What if I had a negative first coefficient and a positive second coefficient?
Yeah.
So is the negative common to both terms? No. But there is a convention that we follow in mathematics where if the first term is negative, factor out the negative. You always want that leading coefficient, first coefficient we call it, a leading coefficient, to be positive. Is conventionally what we do. So if I've got the first one that's negative and the second one that's positive, I'm going to pull out that negative as part of my greatest common factor. So then my greatest common factor is going to be what? Carolyn? -2ab cubed, actually. Because I've got 5 b's here and 3 b's here. So the largest amount of b's I can pull out is b cubed. So that's my GCF. And then what we do to find the rest of it is I'm going to divide each term by my GCF. -2ab cubed. If I do that, what do I get? -2 divided by -2 is? Yes, the end result, Harwin, is going to be b squared. -2, good, because +4 divided by -2 is -2. A cubed, and that is it. Absolutely. If it helps to write it like this, so you can do that division easier, absolutely write it like this. So once you pull out your greatest common factor, what you're doing is you're dividing each term by that greatest common factor, and whatever is whatever's left is what ends up in the brackets there. Is this kind of sort of making sense? I'm hearing some and a lot of people ignoring me. So either the people ignoring me are good, or we're hopelessly lost, and I can't tell the difference.
I think I missed a blank. Or maybe you skipped it. Right about there.
No, you did not miss it. I did not write it.
Okay.
Common factoring is the opposite of what that we've been doing already? No. Look what we did here. To common factor, we found the largest number that goes in, and then we pulled it out, leaving us with something that most. It's not common denominator. It's the opposite of. It's the opposite of distributing. Instead of multiplying what's out front by everything inside, we're taking everything inside and pulling one common thing out from everything. We're basically undoing distribution. Cool?
Is there a name for that?
Yeah, common factoring.
Oh.
Yes.
That's the undistributed.
Reverse distribution. No, it's called common factoring. That's literally the whole point of today's lesson.
It's just how to undistribute.
How to undo distribution, yeah.
Okay.
So what I want you to do is I want you to practice this.
Moving on.
What did you just ask?
If we can
Oh, if we have a nap. I thought you asked if we had an hour.
Oh, no.
No, you cannot have a nap. There's only 15 minutes left, and I want you to practice these things. For the sake of, you don't have to do number one. What I want you to do is questions 2 and 3.
Okay.
Do all of this of 2 and 3. That is what I want you to do. Where are the answers? She says. There aren't any. The answers are right here. May the force be with you all. You're doing them all. Question 2 and 3, all. Give it a shot. So, here it is. And the video will be posted, or you can take a picture.